Welcome back. We are proving this important theorem of Galois, which says that a polynomial is solvable if and only if its Galois group is solvable, very simply speaking. So this is the main achievement of Galois, and this is where he solved the problem of insolvability of quintics. And in fact, he did more than that. He gave a very group theoretic characterization of solvability of a polynomial. So using this method, we have the classical notion of solvability of polynomials or expressing complex numbers using radicals, and he connected it to the modern notion of solvability of groups, which he in fact created. Okay, so we proved one direction. Before we continue the proof, let me quickly settle a issue that I last time had. Okay, so this I wrote it already here. So if you remember, when we were discussing quartics and analyzing them and proving that quartics are always solvable by radicals, I did not explain one point when I was doing this. So I don't want to get into the details of the proof, but you can go and see that video. I think it was 1 or 2 videos ago. There we encountered this situation where G is the Galois group in question, and it contains an element of order 3 by hypothesis, because 3 divides order G. This is the assumption that we are making. And then we want to conclude that the polynomial in question, or rather the resolvent cubic of the polynomial in question, is irreducible. In order to do that, we first note that G by hypothesis contains an element of order 3 called sigma, and its image has this property: if sigma cubed is 1, phi sigma cubed is 1. So the order of phi sigma is either 1 or 3. If it is 3, our proof works, and we conclude that it must be a 3 cycle, because it's a order 3 element in S3, so it must be a 3 cycle, which in turn implies that G acts transitively on the set beta 1, beta 2, beta 3, which in turn implies that G is irreducible. But we needed to rule out the possibility that phi sigma has order 1. But if phi sigma has order 1, that means phi sigma is 1. The only element of order 1 in any group is the identity element. If phi sigma is 1, that means sigma is in the kernel of the map phi, right? But kernel of the map phi is D2, as I noted earlier in the proof. Kernel is those things that fix bit i's, but that means that exactly consists of these permutations. But this is a problem now, because D2 is the Klein 4 group. In particular, it has order 4, but order of sigma is 3. So an order, basically what I am saying is that an order 3 element can't be inside an order 4 group. Okay, so phi sigma cannot be order 1. So let me now get back to the main part of the proof of the main theorem that we are doing. I hope that was clear. So that I just wanted to fix that before proceeding, because that I left without proof last time. Okay, now let's get back to this. This is the main theorem that Galois proved towards solvability of polynomials. We proved already that if the Galois group is solvable, the polynomial is solvable. This is sort of straightforward computation. We are now going to prove the converse, and in order to prove the converse, I need to introduce some notions about composite of two fields. And the composite is the smallest field containing both of them. So we have to fix an ambient field K that contains both L1 and L2. Composite is the smallest subfield containing both of them. And the most important case for us is this situation, where both L1 and L2 actually are extensions of a fixed capital F generated by alpha i's and beta j's. Then the composite is simply generated by the union of these things. Okay, I already wrote this. This is new. So a good example, in fact this is sort of the typical example that you have to consider, is if you have L1 is q root 2, L2 is q root 3, then all you need to take for the composite is q root 2 comma root 3. Okay, so this is the composite. It's just a fancy name for something you are very familiar with. And last time I left as an exercise for you the statement that composite of two Galois extensions is Galois. This is not difficult. This is just standard Galois theory. So in fact I gave you a hint which more or less solves the problem. So now let me do a couple of more propositions which are needed for the converse of our main theorem. Suppose we have two radical extensions L1 and L2. I claim that their composite is also radical. Okay, so now just a word about the ambient field. We need an ambient field K containing both L1, L2 in order to make sense of the composite. Right, because without this ambient field which contains both L1 and L2, the composite just doesn't make sense. Okay, but otherwise the ambient field is irrelevant. Okay, so often we can take K to be just F bar. So our main situation will be L1, L2 being finite extensions of F. So if you take F bar containing both L1 and L2, this is the algebraic closure of course of F. That will play the role of this ambient field. So in the propositions that I am now going to write, I will not mention this ambient field, but you can work with any field that contains both of them. In particular, you can take the algebraic closure of all three of them will be the same. So let's prove that composite of two radical extensions is radical. Okay, now we know that L1 over F is radical means there is a tower of simple radical extensions where the last field in the tower is L1. So I'm going to write it like this: F contained in A1 F adjoined A1 A2 and all the way up to A1 A2 AR. This is L1. Okay, now what is the property? This is simple radical. That means A1 power N1 is in F. This is also simple radical. That means A2 power N2 is in FA1. Right? So this was something that we called F1 earlier. This we called F2. This we called FR. But I don't want to introduce that kind of notation now. I want to keep track of these radical elements that we attach in this tower. Okay? So we have a series of radical extension, simple radical extensions ending with L1. So similarly, L2 over F is radical implies we have also a similar tower. So F contained in F of B1, contained in F of B1 comma B2 and all the way up to Bs, which is L2. Okay, so this is simple radical, this is simple radical, this is simple radical, this is simple radical. Okay, so radical extension is simply by definition a tower of simple radical extensions ending with whatever field you started with. Now we know by the analysis that I did in the previous slide and in the last class, the composite is simply F adjoined the union of these generators. Okay, so I claim that this is radical over F and the tower of simply radical extension is staring right in front of you. Okay, so what do? We do first B1 through Bs minus 1. So this extension is generated by Bs, right? Because all the other things are common. So if you take this as the base field, this field is generated over this base field by Bs. And we know that Bs power some Ms is in, right? This is by definition because this is simple radical. That means Bs is the last attached element. So its power is in the previous field, which is this. But of course, this is contained in this bigger field, which is exactly what you see here. So this is simple radical, right? So now we leave A1 through AR as they are, but remove Bs minus 1 from this. So this is also simple radical because Bs minus 1 generates this over this and this belongs to this. Okay, now you keep going like this. So don't disturb A1 through AR. Okay, so the previous one will be generated by B2 and some power of that will be in this, right? So this is simple radical also. So all of these are simple radical. Now you consider this. I claim that this is also simple radical because b1 power m1 belongs to f, so it certainly belongs to this. So this is simple radical. And now you just put this tower underneath this. So just to spell it out, I get a1 through ar minus 1, a1, a2, a1, f. All of these are simple radicals. Of course, this part is just this part. This is just star. This is, if you call this the second one star star, this is star star after adding a1 through ar to every field. Right? So you take star star and add a1 through ar. So if you take a radical extension, tower of simple radical extensions, attach some say common elements to all the fields in question, it will remain simple radical. So that means, so the conclusion of all this is, L1 L2 over F is radical as we need. Okay, so this is just an easy observation, but it's good to make this and repeatedly use this. So composite of simple radical extensions is simple radical. Let me do one more proposition. This is in fact a very important proposition that we will often use. Okay, so let L over F be a radical extension. Let L over F be a radical extension. Then there exists an extension K over L such that two things happen. K over F is Galois and K over F is radical. Okay, so any radical extension can be extended further to get remain radical, but now the new thing will be Galois. Okay, so this is given, L over F is given. You can construct one which is Galois plus radical. So, and this is going to be very useful to us, and often we will apply this because often we want to work with Galois extensions. So if you have a given radical extension, it may not be radical, but we can always extend and get Galois plus radical. So in proofs that will come later, given a radical extension, we might as well assume that it is Galois without loss of generality. Okay, so the construction of K that will do the job for us is fairly straightforward. Okay, so I should also remark here that I am going to assume characteristic 0 throughout for the rest of the course. So I am in fact going to work generally with subfields of C. Every field that we consider is subfields of C and their finite extension. So they also will be contained in C. Okay. So now let's go ahead and prove this. This is also sort of easy application of the previous proposition and the exercise that I gave here. So what do we do here? So first L over F is radical. So we can write just like in the previous theorem proposition, we have F contained in F of let me call alpha 1, F of alpha 1, alpha 2, all the way up to F of alpha 1, let me call that alpha n, which is L. Okay, so the point is this is simple radical, this is simple radical, this is simple radical. Simple radical, remember, let me remind you, is that alpha 1 is some power root of an element of F. So that means alpha 1 power some n1 is in F, alpha 2 power n2 is in this field, and so on. Okay, now we are going to take basically, so let me write it like this. So let S be the set of all conjugates in some larger field, in some extension of L. For example, in L bar. Okay, so you can take L bar, the algebraic closure of L, and conjugates. What is the meaning of conjugates? So conjugates of alpha 1 are the roots. So it really, I should say, F conjugates. F conjugates. Conjugates of alpha 1 or F conjugates of alpha 1 are roots of the irreducible polynomial of alpha 1 over F. So you do that for alpha 1, you do that for alpha 2, and you do that for all alpha n, every one of them. So it's a finite set. Alpha 1 may have 25 conjugates, alpha 2 may have 31 conjugates, alpha 3 may have 5 conjugates. You take all of them and call S. Okay. So now let K to be F adjoint S. So attach all of them. So I claim that, so we claim that K is the, so of course K contains L, right? Because L consists of alpha i's. So S is a superset of, rather I should write it like this. If in fact Fs equal to L, that means all conjugates of alpha I are already in L, which will imply that L is already Galois over F, so we don't need to do anything. But in general we have to add the extensions, conjugates. It is the required extension, so that K, if I put, that means K over F is Galois plus radical. So let's prove why that is the case, and that proves of course the proposition. Okay, first I want to show that it is in fact radical. Why is it radical, or actually why is it radical requires a little bit work. Galois is easy. It is Galois because let's say Fi is the irreducible polynomial of alpha I over F. Then K is the splitting field of F1 through Fn, I think I called, over F. Right? This is easy because you take the polynomial F1 through F1 times F2 times Fn. This splits completely in K because you have attached all the roots of these polynomials to K. In fact, K is generated over capital F by those roots. So this is certainly the splitting field. So being the splitting field of a polynomial, here we are in characteristic 0, so it is Galois. Okay, so this much is okay. Next we want to show that K over F is radical. Okay, this is done in the following way. So I want to produce a, first of all let's look at the following. So simple observation. So we first want to make an observation. Okay, so suppose you have, okay, so what I want to observe is the following. Suppose you have F inside F alpha is a simple radical extension. So that is alpha power n is in F, let's say. So forget the earlier notation, I am just taking a simple radical extension with this property. Now let sigma, so suppose basically I will take, this is contained in L. Okay, so now let F alpha be in L, and sigma from L to L, sigma from L to, actually I don't care what that is. So let's say sigma is a function from F alpha to some L, be an F homomorphism. So it fixes F, but it sends alpha to something. Then, so apply sigma to this inclusion. What do we get? What we get is sigma F contained in sigma of F of alpha. But this is F, of course, because sigma is an F automorphism, this is F. So this is nothing but F of sigma alpha. Okay, because again F is fixed point was, so the extension is generated over F by sigma alpha. So now sigma alpha power n is in F, but what is sigma alpha power n? This is sigma alpha power n, but alpha power n is in F. So this is in F, right? So in fact, sigma alpha power n is equal to alpha power n. So sigma of alpha power n is again in F. So the conclusion I want to draw your attention to is, given that this is simple radical, this is also simple radical. So we conclude F contained in F of sigma alpha is also simple radical. Okay, so this is the crucial observation. Now let's get back to the proof that K over F is radical. So you have now, let me write this down. F contained in F alpha 1 contained in F alpha 2, sorry, F alpha 1 comma alpha 2, and all the way up to alpha 1 through alpha R or alpha n, which is our L. And now let G be the Galois group of K over F. K is already proved to be a Galois extension of F. Let's take the Galois group of that extension. So let's say G is sigma 1, sigma 2, some sigma R. Okay, so some collection of automorphism, right? So it's an extension of degree R. So apply, so this is sigma 1 is identity. So think of this as the one with sigma 1. Apply sigma 2 to this inclusion. Apply sigma 2 to this inclusion. What do we get? Sigma 2 is an F automorphism. So you get F, sigma 2 of F is F, but you get sigma 2 alpha 1, F of sigma 2 alpha 1, sigma 2 alpha 2, F of sigma 2 alpha 1, sigma 2 alpha n. This is actually nothing but sigma 2 L, right? So K, it is an automorphism of K, L is contained in this, so it will go to sigma 2 L. L is of course not normal, so it will potentially be some other field. Okay, but the point that we can now conclude using this observation that I gave here is, these are simple radical by hypothesis. But now we conclude that this is simple radical because some power of this is here, some power of sigma 2 alpha 2 is here, same power in fact. So now you can apply this to all of them, sigma R finally. So you get F contained in F of sigma R alpha 1, contained in F of sigma R alpha 1 sigma R alpha 2, all the way up to F contained in sigma R alpha 1, F adjoint sigma R alpha 1 sigma R alpha n, which is of course sigma R L. The same logic tells you that these are all simple radical extensions, because sigma R alpha 1 power something lands here, sigma R alpha 2 power something lands here. Similarly, sigma R alpha n power something lands in the previous field. So now this is an easy exercise for you. K is actually the composite of okay, so I'll let you do this. If you take, this is called the Galois closure. So this is in some sense the smallest the smallest Galois extension containing L. Okay, so because you have to attach all the conjugates of alpha I, you have no choice in order to get a Galois extension. So Galois closure is nothing but the conjugate of these, because remember K is equal to hint Fs. What is F? What is S? S consists of alpha 1 through alpha n, sigma 2 alpha 1 alpha n 1 to sigma 2 alpha n, sigma r alpha 1 to sigma r alpha n, all the conjugates. So this is as an easy observation, because the conjugate of all these fields is F adjoint union of this and this, that is same as this. Okay, now we are done. So since we are now done, since L over F, sigma 2 L over F, sigma R L over F are all radical, right? Because by the way we constructed these, right? Sigma 2 L is radical because there is a tower of simple radical extensions ending with sigma 2 L. Similarly, sigma R L is radical, right? So this is because of these towers. So they are all radical, and composite of radicals extensions is radical. I proved that composite of two radical extensions is radical, but one can quickly check that composite of three radical extensions is radical. That is, you do two and then do one more. Okay, that is triviality. So after you take the composite of all of them, you get K, and hence K over F is radical. We already showed that K over F is Galois. So given a radical extension, we can extend the extension to preserve radicalness but add Galoisness. Okay, so given that, we have now a radical Galois extension. Okay, now we are ready to prove the converse of our main theorem. And recall, what is the main theorem that we are trying to prove? We are trying to prove that G Galois group of a polynomial is solvable if and only if F is solvable. Okay, so we already showed. So this is our theorem, stripped of all the notation. Okay, so I will urge you to go to the statement of the theorem for the notation. Capital F is a subfield of C, small f is a polynomial over capital F, and then we have this. We already proved this, right? We already proved that if Galois group of the polynomial is solvable, the polynomial is solvable. Now we will prove this direction. Okay, so let me just make sure that I got these implications correct. So G is solvable if and only if F is solvable. Assuming G is solvable, we showed that F is solvable. Okay, now we are going to show that if F is solvable, the Galois group is solvable. Okay, so let me end the class here. In the next class, we will complete this proof and then see what kind of implications it will have. Thank you.